In this video, we're going to discuss the divergence theorem. So the divergence theorem is essentially the three-dimensional version of the flux form of Green's theorem. So just to remind you, right here, this is Green's theorem. And so when we were evaluating integrals using Green's theorem, we had a plane region, and it was enclosed by a smooth oriented curve C. Now this is going to extend using the divergence theorem into a solid region that we're going to call D, and it's being enclosed by a surface, an oriented surface S. So our theorem, what it says is we take the double integral over our surface S of our vector field dotted with the normal vector, and that's equivalent to the triple integral over our solid region D of the del operator dotted with our vector field. And so just to mention here that our vector field has continuous first partial derivatives in our region D, and then also it is enclosed again by our surface S, and then N is the outward unit normal vector on S. Okay, so let's take a look at an example. So we have our vector field defined here as x sine y, comma negative cosine y, comma z sine y. And S is going to be the boundary of the region that's bounded by these particular planes. We have 5 planes here: x equals 1, y equals 0, y equals pi halves, and z equals 0 and z equals x. So for our divergence theorem, we're going to end up using the form where we have this triple integral over our region D, and then we need the dot product of our del operator and our vector field. So let's start with the integrand here. So the del operator is basically just taking the partial derivatives. So when we dot this with our vector field, we're just going to take each of the partial derivatives. So the partial derivative with respect to x of our x component of our vector field, then because we're doing the dot product, plus the partial derivative with respect to y of the y component, plus the partial derivative with respect to z of the z component. And this is going to be the integrand of our triple integral. So with respect to x, sine y is just a constant, so we have sine y. Now with respect to y over here, we're going to take the integral, or the derivative of negative cosine, so that's going to give us sine, so plus sine y, and then the derivative with respect to z, sine y is a constant, so that's just going to be sine y. So we end up with 3 sine y. Okay, so plugging this into our triple integral, and we're going to put our limits of integration next, we have 3 sine y. Now we have our region bounded by these planes, and so what we can do with our triple integral is just integrate with respect to x, y, and z in the best order possible. Because z is a function, or is a function of x, we're going to integrate with respect to z first, so z dz here, where z ranges from 0 to x. Then next we have a choice between y and x, and the next best choice would be to integrate with respect to x and then y. So if we integrate with respect to x, we know that we're bounded by the plane x equals 1, but we also know that z equals x and z equals 0, so the lower bound for x is 0. And then last, the boundaries for y are 0 to pi over 2. Okay? So for our integration, first we're going to look at z. So integrating with respect to z first, we have 3 sine y times z from z equals 0 to x. Alright, now what that gives us is 3 sine y x, it's going to be minus 0, so we don't have to write that, and then dx dy. And then let's put our limits back on. From x was from 0 to 1, y was from 0 to pi over 2. Okay, now integrating with respect to x, 3 sine y is a constant, so we're going to get 3 sine y times x squared over 2, evaluated from x equals 0 to 1. Alright, so plugging in 1, we get 3 sine y times 1/2, so I'm going to go ahead and put the half over here, and then when we plug in 0, this is all going to go to 0, so we don't need to write that. And then last, we can integrate with respect to y. Okay, So with respect to y, the integral of sine is going to be negative cosine, so negative 3/2 cosine y, evaluated from y equals 0 to pi over 2. And then the last step, plugging in for pi over 2 and 0, we have negative 3/2 cosine of pi over 2 minus cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. So this is going to be negative 3/2 times negative 1 with the final answer of 3/2. Alright, so the last thing to mention here is the divergence theorem for hollow regions. So if you have a region D that's bounded by a surface S, but it's hollowed out, so think of it sort of, I know my drawing is not donut-like, but think of it almost like a donut, where you have this hollowed out center. So you have this surface bounding the inside, the part that we're going to hollow out, and then a surface bounding the outside. And so S is the union of these two. So you can think of S as this area here. Okay? So if this is the case, if you have a hollow region, then your divergence theorem basically just has to account for these two surfaces. And so what you end up doing is you take the double integral over the outside surface, or S2, the outside surface, S2, and subtract the double integral of this inside surface. And then in this case, this is where the normal vectors n1 and n2 are the outward normal vectors for each of the surfaces. So you could think of n2 as an outward normal vector from here, and you could think of n1 as an outward normal vector from here, from this surface.